this is this is a different presentation from the one you found this morning on the agenda, because as Simon mentioned, the person couldn't reach us. So this is a presentation that I have already done in a couple of other places. I presented it also last week at a different meeting. So it's an excerpt from a longer workshop that I had prepared, and it's about ASPA. It's about a new object that you find in RPKI that can help in doing ASPA validation. So it was ready, and we had it. So started. I thought, why not do it here now, because we have a slot. So thanks. Yeah, I see the timer is screaming at me, but it will be fixed. So before we can start talking about ASPA in detail, it's better to start with a quick introduction about RPKI and what it means. So in BGP, we have networks that try to talk to each other, and they exchange information using BGP. They send BGP updates, which contain information about networks they are originating. And one thing that we have is we want to build knowledge about where to send traffic for certain destinations. But when we do that, we need to use facilities that are not there in BGP. BGP was built to be way simpler as a protocol, so it just gives us a way to send information to the other side, but it doesn't give us ways to verify that data. So we have to introduce something external to answer certain questions, which is like, can I trust these people? So we have a database, external, that was built as a concept more than 30 years ago. And this gives us like answers about like where data could be originated, or who is supposed to be originating certain networks. So the problem is, though, that we have more than 30 of those registries, and we have problems in trusting them. Many of them, it's very simple. You just pay a fee, you get a maintainer, and then with that, you can create objects if people have not already created objects in that address space. So you can relatively easily hijack address spaces with that. I had an example, because I run my own network, and I went to a place as a bring your own IP addresses for them to be announced on the internet, and basically they had proxy created an object in one of these databases for me that I couldn't even remove after that, after I stopped using their service. So we have a problem. Some internet routing registries cannot be really trusted. There's problem about accuracy of data. In some places it's incomplete, lack of maintenance. I was writing a little piece of software some years ago when I was at the Internet Society to verify some IRR data. And I had a colleague from Mauritius. And we said, OK, why don't we use Mauritius as a country to test if the logic in my software is correct or not. And I spent 2 days trying to debug that, because it seemed not to be working. And after that, I discovered that none of the networks in the country had data in the appropriate database. So we have a very large problem with third-party databases, other sources. So in 2008, people came up with the idea, let's put an additional piece there to verify the data that we see in BGP. And that's when RPKI was started. So the idea is to add a little bit of cryptography on top of whatever we already have, and give us data that we can finally trust. So the idea was to take what we have, IP addresses and origin ASNs, but the idea was at this point to follow the hierarchy of the regional registry system. So we have 5 entry points, and that's it. We don't have any other external databases. And then the final goal at that point was, let's make it so that we have, in the end, statements, a piece of file that tells us, and we can verify, that tells us that this network should be originated by this ASN, and there's a signature from the holder of the address space. So this is how RPKI started, and they built it as a framework where you have 5 entry points, the 5 regional registries. They can also have delegated RPKI, but that's a different story. And we have objects that are put into these regional registries. There are ROAs, there are others now. And with the validator, a software that we can run in our networks, we can get this data, put it together, and then find a way to push it to our routers. So looking at it from a different perspective, we have the validator. We have a validated cache, which is where we look at all the data into the ROAs. We look at all the certificate chains, if everything matches, if everything is okay, and then we put it into that validated cache. So we only have the ROAs that are valid, where all the signatures are okay, where all the certificates are fine. And then we pass it on to our routers, and we help these routers make better routing decisions. So with this, let's go into a little bit more detail about what a ROA is. And it's a file that contains basically 3 things. We'll see them in the next slide. But the final thing is it's an authorized statement from a resource holder. Somebody has a network and says something could be done with that network. And we have 3 pieces of information. We have the prefix, we have the origin ASN, and then when they were designing the protocol, they thought about me, and they added a max length, an attribute with my name. They added the max length to, basically the idea of the max length is if I have a large network, if I have, say, a /16, I can make one statement and say, this ASN is allowed to announce anything from /16 to /24 in this area. And I can use it to make my life a little easier, but there are drawbacks when we do that. And that's for another talk. So where do we go from here? ROAs give us just one way to look at things and only give us origin validation. So the paths are not validated. So we need more building blocks here. And we have RPKI objects, we have ROAs. And then over the course of time, there was another standard that was developed, and it's called BGP-SEC. Has anybody ever used it? Or no? No one. Do you have any idea why? Is it really terrible? It is not terrible, like it would be the final answer to figure out path validation. Where is the problem? CPU, exactly. So what BGP-SEC does is sign every single AS path in a BGP update. And then you have to verify those signatures. Basically, you would have a chain like the one here. Would have network 1, receives a BGP update, looks at the AS path. Let's say there's no BGP-SEC signature yet. So what it does, it adds a signature of the AS path, adds a link to his key in the BGP update, sends it over to network 2. Network 2 gets the AS path, validates the signature, so opens up, validates the signature from network 1. If everything's okay, it adds its own signature, its own key pointer, and then passes on to net 3. And net 3 has to do twice the validation, because it has to validate the path from net 2, then it removes network 2, and it does the validation from network 1. So now this means that on an average day, where the average AS path on the internet is 7 ASNs long, for about 1 million routes in the full routing table, so I would have to do roughly 7 million verifications of the chain of trust, where each one of them requires downloading a key and performing cryptographic evaluations. That doesn't work. So BGP-SEC would be the ultimate answer, but for now, I would call that the future. And that's something that might be in 10, 15 years, probably. So looking back at our situation, we have ASPA that was brought in just recently. Actually, it is the present of RPKI validation, not really the future, because we can use it these days, not everywhere. We'll see it in a moment. But it stands for Autonomous System Provider Authorization. It's a new kind of object in RPKI, very, very simple. The ITF work is still in draft. There are two separate drafts, one that defines the object and one that defines how you should be doing the validation. But they are at a very late stage, so they should become a finalized document soon. So if I look at it from a very simple perspective, this is what it looks like. You have an ASPA for an AS number, and it should contain just all your upstreams. And when I prepared this presentation, I got to this point. I said, well, I've said it all, so it could finish here. So we could actually have a break. We could actually have a couple of beers before the next talk. It's not all here, but this is all you need to know to understand how ASPA works. You just have to create this object and list all your upstreams, not the peers, just the upstreams, just those you buy transit from. Not your peers at an IXP, not your peers on a PNI, nothing else. So it's very simple, and it takes 30 seconds to log into the RIPE-NCC portal, go in and add your ASNs as a list to your ASPA. But digging a little bit more, so they're distributed as part of the RPKI dataset. So there's already a whole infrastructure that's supposed to be doing that. They're signed. They're supported in a protocol called RPKI RTR version 2, and that is also in a draft state. They decided, though, to not do a new draft, but they're taking the old RFC, RFC 8210, and call it RFC 8210 bis. And as of now, it's available on RIPE-NCC as hosted RPKI, the RN-hosted RPKI, and APNIC should be at the end of Q2 2026, so soon. And then you can do delegated RPKI, so you can run your own software to do your CA and your publication point, and then you could just implement it. And every ASN should have one of these. So how does it work in reality? So we filled in our information, our object, and imagine if in the world everyone had filled in those information, we could then build a graph of all the relationships of on the internet. Who is a transit of who, supposedly according to ASPA. So we would have ASPA A and ASPA B, and on the top, you see we have ASPA C. Does it work? Yes, I just had to be patient. So ASPA C has AS0 as its ASPA there, which means I don't have any upstreams, and we'll see it in a moment. So if I look at this, I can go from both sides, and I have a whole path. So I go from customer to provider to other provider down to provider and customer. And with this, I basically get two things. Somebody mentioned it. It was mentioned this morning already. There is what's called an up ramp and what's called a down ramp. So when you look at ASPA, you always will have a part where you go up one side and then you go down the other side. They can be different in length. They can be the same length, but you have two different ways to verify those. And I won't go into those details, but you have to know that there is an up way and a down way always. And basically, we have three states, like in RPKI. We have a state that says provider, where the ASPA exists and defines that ASN as an upstream of another ASN. There is a situation where something is not provider, so the ASPA exists, but it doesn't define that as an upstream, so something is wrong. And then we have the last one that says no attestation. We don't have an ASPA. We can't really verify this data. So we have different situations. So As long as you don't have any not provider in your chain, things should be fine. This helps in failing open. Basically, you can have parts where maybe you have a whole up ramp that is fully verified, but you have a down ramp that is not. And then you would still have a situation where things are okay, should be okay. You can send traffic there. We don't have a way to verify the other side. So for now, when can you do validation? You can do it in BIRD, OpenBGPD. You can do it in Cisco iOS XR, which is still in testing, and actually Switch is testing it for Cisco. And then I was told literally 30 minutes ago that Arista should be ready at the end of June.
Nokia is on the roadmap.
And Nokia has it.
Until end of the year.
Yeah, and then other vendors should have it already in their roadmaps. Routinator and RPKI client includes support for ASPA already. Routinator needs to, you have a flag you have to enable to add ASPA, but that's fine. So you've seen that I've used AS0. And AS0 is a way to say I have no upstreams. Make sure no one treats me as a downstream for someone else. You could use any other BOG on ASN, but AS0 is the one that's easily recognizable. It's a standard that's being used and should be seen used by tier ones, so operators that are at the apex who don't buy any transit, but also IXP route servers or route collectors. So I checked yesterday, so I was looking at some of the numbers, and there are 1,800 ASPAs, and among them, 26 have an AS0 as a declaration. So that could be something nice to investigate by the next year, just give more data. So how can ASPA help in verifying the data? Imagine we have a situation like this, and another A appears on the other side, somebody claiming to be A from my left side, but their ASPA for A doesn't declare D as an upstream, so I can immediately spot it. And I can say, okay, I'm not receiving this BGP announcement because A is not supposed to be using D as an upstream. So I can easily clear it out. And then I could have D talking to C, which is its upstream, and then somebody tries to get in the middle. E tries to get in the middle, and I can spot it because D doesn't list E as its upstream. So in that case, E to C would be valid, but D to E would not be. So I can take that BGP announcement that contains this AS path, and validating it with ASPA, I could just say, no, I'm going to not accept it, and just leave that route out. And then another example could be when we have, this is a normal path, but we insert an IXP in the middle. Whoops, let me go back. We insert an IXP in the middle, and how do you think this would work? I had a specific question about this last week. So if I insert an IXP in the middle, people would say, okay, if I look at ASPA, B is not an upstream for E, or E is not an upstream for B. That's fine. But since we check on the one side, we check the up ramp and we check the down ramp on the other, they both validate, and they are basically they both validate E to B. They don't contain anything. They're just exchanging traffic. They're just on the same level. Then they are fine. They are going through an IXP. They're going through a PNI, and this lowers the up ramp and the down ramp and just gives us a lower value. But that's it. Then it validates. I hear some confusion because I hear so much silence. I hear confusion. Yes, it's a matter of length of the up ramp and down ramp. It's a matter of checking how the relation. So basically, in this case, when you do the validation, let me walk you through a bit, and we should have a bit of time. When I do the validation for the up ramp, so I do A to B, and that's fine because A lists B as an upstream. B to E it breaks because B doesn't list E as an upstream. That's fine. So let's put it there. So we have found our up ramp. On the other side, we do the same kind of validation. D to E validates because D lists E. E to B doesn't because E only lists C as an upstream. But then B and E are both at the apex of their ramp. So when they talk to each other, that's fine. And they don't represent a transit for each other. So they're just at the apex of the two ramps. And this means we can validate the path and it's perfectly fine. And I hope this helped. Yeah. But then we have a situation where we would have valleys. Imagine we have E to B, and then someone tries to hijack them, or even worse, at one point in time there was a dispute between two large networks. And they disappeared between each other. So they stopped talking to each other. But turns out that in that case, there was a tiny ISP in the middle of nowhere in the US that hadn't updated their filters. And basically, it was acting as a transit between the two networks. So when you have a situation like this, how do you think that would work? This would be both invalid because E doesn't list C as an upstream and C doesn't list B as an upstream. So you would easily identify when there's a hijack like this, or where there's a case somebody has misconfigured their filters, because you would see that valley in your AS path and you would be able to filter it out. So this would help in a case where somebody would be misconfiguring or trying to hijack in the middle of nowhere. Make sense? Yes? No? Okay, so wrapping up. We have these three objects, and actually we have a fourth one that's already there. That's the RPKI signed checklists that also add information to RPKI. Basically, you can, with signed checklists, you can take a file, have it signed, sign it, and then use that as proof that the file is connected to your networks. So you have a /16 that you want to announce somewhere, and you have to send an LOA. You can sign the LOA in a checklist, put it in RPKI, and tell the person on the other side, hey, I signed it there. You can verify the signature, and with that, you will verify that it's the same certificate, the same CA that signed that network. So you know that I'm allowed to originate or do something with that network. In reality, we could put anything in a signed checklists. We could sign anything, any piece of data. And the idea is that those could be used for other purposes later on in RPKI, so we can do more. So hopefully, we can leverage all four of these objects in the future to add more security to routing. So what is ASPA in the end? It's a new building block, a new thing you can have in RPKI. It helps making routing more secure. It still needs to be widely adopted, but where can you start? I would start by creating your ROAs and your ASPAs. That's relatively easy. You just have to log into your RIPE-NCC portal, and then you go into routing security, and then you create those objects. It really takes like 5 minutes.
I just did it.
Yeah, well, 2. 5 if you have to figure out how to do it, and you have never logged in. But yes. Then the next step would be evaluating relying parties. When I say relying parties, I mean the software that does the validation, the validators. You need at least 2 of them in your network. There are 3 of them, actually 4 you could run. You could run Routinator, you could run Fort, you could run RPKI client. And then there is also an additional piece that I called RTRTR that you could run with RPKI client. And my suggestion would be to start logging and not filtering based on ASPA. So gives you a way to check your customers, how they're doing, and also check the rest of the internet. there is, it was mentioned in the talk this morning that there are certain paths, there's a small percentage of paths that are not, well, they come out as invalid in ASPA. So I would start having a look at those and see if they involve any of your customers, any of your routes. So I would start from there. There is a recommendation that was given initially with RPKI that was tag your RPKI validation state into a community. I would not recommend doing that, especially now for ASPA, because ASPAs change more often than ROA states. So that would increase the number of BGP updates in the wild, so I would not do that. But I would start logging whatever you find with ASPAs. There is a software written by Andre at RIPE-NCC to validate, visualize ASPA and ASPAs in the validation states. So I would start having a look there as well. Then there is BGP Alerter that I would start using to keep an eye on how my routes are and how my BGP is doing. And there are two versions. You can run the open source version directly from GitHub, or you can go on packetviz.net and get a commercial service that does that, and it uses the open source version. And then if you have any questions, I'm here.
Thank you.
I think we have one.
Huh?
Do we have time for one question?
Let's do one. We're slightly behind schedule.
Hi, Sylvan here. One question to your slide with the how to get started. Can you also add that you should nudge your customers to sign their ASPA as well?
Yeah. Good point.
Okay.
Nothing? Well,
Just a statement, really.
yeah, then finished.
Good.
And
Thank
if you
you.
find a language that I don't have yet, please let me know if you know of that.